off, we hadn't calculated the standard deviation yet, but the standard deviation of the bonus is going to be the square root of the variances, right? So square root of the standard deviation squared, that's variance, plus standard deviation. And remember, this stands for bonuses of cars sold and bonuses of cars leased, right? So let me plug everything in. This standard deviation was 471.5 squared, plus this standard deviation was 192. All right, so let's square these. All right, so I'm going to put this in my Desmos app. All right, 471.5 squared. All right, so I end up getting, I skip the step, and I end up getting 509.09. And that is my standard deviation, the square root of the combined variances. All right, so this problem was big and it was hard. What we did was we transformed both of these means and transformed both of these standard deviations and then combined them. So we basically did everything in the packet in this one problem. All right, now I want you to pause the video and try example 2 on your own with combining. All right, so pause the video, come back, and we'll work through it together. Okay, I don't like this example. Number 2. Mr. Patterson has been dying to use his silly foam grammar hammer on someone who makes a lot of spelling and grammatical errors, and he made the huge mistake of hitting Miss Lucas with it. Miss Lucas says she hardly makes any errors, but unfortunately for her, Mr. Patterson did his stats homework. He says smugly to her, typographical and spelling errors can be classified as either non-word errors or word errors. For example, your December 2nd notes include the non-word error, TEH, and the word error, loose, when you clearly meant lose. In fact, I analyzed all your statistics class notes and calculated the number of non-word errors X in a randomly selected guided note packet to have a mean of 2.1 and a standard deviation of 1.136. The number of word errors Y in the same packet has a mean of 1.0 and standard deviation of 1.0. Yo. All right, that was my impression of him. All right, calculate and interpret the mean of sum S, which is X plus Y. So remember, Mr. Patterson smugly said that X was non-word errors in my guided note packets, and Y is word errors in my guided note packets. All right, so for X, he said mean of 2.1 and standard deviation of 1.136. And Y has a mean of 1 and standard deviation of 1. All right, so calculate and interpret the mean of the sum of S. So remember, if I'm finding the mean, it's just going to be the sum of the two means when I'm combining. So the first mean was 2.1 and the second mean was 1. So when I combine them, I get a mean of 3.1. So if I review many, oops, guess I just made a word error there, of Mrs. Lucas's guided note packets, I expect to find 3.1 word and non-word errors per packet, which is entirely false and libelous. All right, calculate the standard deviation of the sum S, which is X plus Y. All right, so the standard deviation of S is going to be the square root of the variances, right? So I don't have the variances, but I can find them. My first standard deviation is 1.136, so I would square that, plus the second variation, standard deviation squared. All right. So I see that 1.136 squared is going to give me 1.290496 plus 1. So I'll add those together and take the square root. I'm going to go ahead and do that in my Desmos app while you do it in your calculator. Okay, so I did the calculation in my Desmos app and I got 1.51 for the standard deviation of the sum. So here's my interpretation. Again, I do not agree with this interpretation at all for its validity. The sum of the word and non-word errors in each packet typically varies by 1.51 errors from the mean of 3.1 errors. Again, remember, standard deviation is typical variance from the mean, right? Okay, now I'm going to do a real blast from the past with normal distribution probability review. This is our last section. All right, so remember, here's our empirical rule. 68% of the data is within 1 standard deviation, 95 is within 2, and 99.7 is within 3. Remember our z-square formula, value minus mean over standard deviation is equal to z. And z is the number of standard deviations above or below the mean that a certain value is. Okay? Hey, dogs. Shh. All right, example 3. Miss Lucas finally saw us this weekend. After jumping in her seat multiple times, she wondered how the soft drink in her hand didn't spill all over her. She was so curious she decided to do some research. The diameter of C, the top of a randomly selected large drink cup at the movies, follows a normal distribution with a mean of 3.96 inches and a standard deviation of 0.01 inch. Draw the distribution below. All right, so I have a normal distribution. My mean is 3.96 inches, and I'm going to have 3 standard deviations above and 3 standard deviations below. And then if it's a normal distribution with a mean of 3.96 and a standard deviation of 0.01. So all I'm going to do is add 0.01 each time. So I'm going to start off with 3.96 plus 0.01. This gives me 3.97 plus another 0.01, 3.98, and then 3.99. If I go down, it should be 3.95, 3.94, and 3.93. Sorry, I made it a little crowded there. All right, what is the probability that a randomly selected large drink cup will have a diameter larger than 3.982 inches? All right, 3.982 will be about here, and it says larger, so I'm going to shade to the right. So I'm trying to find this area, right? So that would mean my value is equal to 3.982. Let's plug it into the z-score formula. So z equals 3.982 minus the mean of 3.96, all divided by the standard deviation of 0.01. All right, so calculate the z-score and then look in your table A and find the number. I want you to figure out if you should take the number from table A or do 1 minus table A by looking at this drawing up here. So once you figure that out, come back. When I did the calculations, I got a z-score of 2.2, which makes sense with my drawing, right? 2.2 standard deviations above the mean, which puts me at the exact spot in the normal distribution curve that I thought I would be. So then I go to the table A, and I'm going to bring that up for you right now. And I'm going to find a z of 2.20, which I go 2.2 here, and it's the first column right here, because that would be the 0 on the end. So I get 0.9861. So if I'm looking back, I get my probability of a z-score of 2.2 is 0.9861, which would be 98.61%. Does it look like 98.61% of that curve is shaded? No. My table A gives me to the left, right? So in order to get to the right, I need to do 1 minus my value that I got in table A. So 1 minus 0.9861 gives me 0.0139. 1.39% of the time, I'll get a drink cup that will have a diameter larger than 3.982. All right, now you're wondering, what does this have to do with anything in the packet? You will find out soon. All right, so on the last page here, example 4, the diameter L of a randomly selected large drink lid at the movies follows a normal distribution with a mean of 3.98 and a standard deviation of 0.02. Draw the distribution below. All right. So I'm going to do the same thing. Normal with a mean of 3.98 and a standard deviation of 0.02. So this is 3.98. And again, my drawing is terrible, but you will have to live with it. All right, so 3.98 plus 0.02 gives me 4. So it'd be 4.02 and 4.04. If I go the other way, 3.98 minus 0.02, I get 3.96, 3.94, and 3.92. All right, so here's my normal distribution. And again, we're talking about drink lids, right? Before we were talking about the cup. Now I'm talking about the lid that goes on the cup. So, what is the probability that a randomly selected drink lid will have a diameter less than 3.973? All right, so the words less than and 3.973. Let's see, 973 would be about here, I'm guessing. And if I want less, I'm going to shade to the left. All right, again, we just use the z-score formula. So z equals 3.973, which is our value, minus the mean of 3.98 divided by 0.02. Go ahead and calculate that and then use the table A. I would expect to get a negative z-score because my value is below the mean. All right, so come back once you've calculated the probability of the shaded area. Okay, so my z-score was negative, which I expected. So this value is 0.35 standard deviations below the mean. And I go to my table A and I get a probability value of 0.3632, which makes sense. This looks like 36% of the curve, so I leave it as is because I've shaded left. All right, now you get to find out what all this normal distribution review has to do with anything. All right, transforming normal random variables. Any sum or difference of an independent normal random variable is also normally distributed, meaning we can use our table A. So assume that C from example 3, the cup, and L from example 4, the lid, are from the same movie theater and are independent random variables. Let random variable D for difference, right, be L minus C, the difference between the lid's diameter and the cup's diameter. All right, calculate the mean of D. So the mean of D is just going to be the mean of L minus the mean of C, right? If D is L minus C, let me put that up here so we remember D is L minus C. We've been doing a lot of sum problems. This is our first difference problem. All right, so the mean of D is going to equal, let's go back to example 3 and see our mean of L was 3.9, or I'm sorry, this was C. So L is up here. So our L mean is 3.98 minus our C mean, which was 3.96. So our mean of D is going to be 0.02. All right, now go ahead and calculate the standard deviation of D. All right, so remember with standard deviation, we're always adding variances. We never subtract variances. So it's going to be the same way as the sums. It's going to be the square root of the variance of the lids plus the variance of the cups. Again, this is not a typo. This is plus. It should always be plus. Variances always add. So when I plug this in, I'm going to get the standard deviation of D is equal to the square root of, so I'm going to start off with my lid standard deviation, and then my cup standard deviation was 0.01 squared. So go ahead and calculate that. Okay, so I calculated the standard deviation, which was 0.02. It says to draw the distribution below, and I've already drawn it because I'm running out of time. So my mean is my new mean here, and my standard deviation is here, right? So here's my distribution. For a lid to fit on the cup, the value of L has to be bigger than the value of C, but not by more than 0.6 inches. So I'm looking for a difference that goes from 0 to 6. So I'm looking for this right here. So you take the z-score of both and then subtract